everyone, a very good evening all of you, and a very warm welcome to you all to the India's largest, the best and your favorite live learning platform BYJU'S Exam Prep. कैसे हैं सब लोग? Can you guys hear me? Am I audible and visible to all of you? Please do let me know through the comment section so that we can start the session at the earliest. As you can see, today we will be having the formula revision for heat and mass transfer. This is the series for formula revision, GATE formula series, which is going to be important for all the mechanical engineering aspirants who are preparing for GATE 2023 examination. So please do let me know if I'm audible and visible to all of you. Can you guys hear me? मेरी आवाज आ रही है? सुन पा रहे हैं आप लोग मुझे? Hi Shivam, good evening. Welcome to the session. So shall we start? This is my introduction for those who are attending the session for the very first time. My name is Chandra Shekhar. I am mechanical engineering graduate from IIT Delhi. Having more than 10 years of teaching experience, I have also cleared engineering services examination and worked in SAIL for a couple of years. Quite comfortable with these many subjects of mechanical engineering. All right. So if you have not joined me on the Telegram yet, please do join me on the Telegram. That is Mechanical by Chandra Shekhar. The link is also mentioned over the screen. Hi Junaid Sheikh, welcome. This is my official email ID. You can contact me through the mail ID if you have anything to discuss regarding your preparation, regarding your subjects. You can always connect with me through the mail ID. All right. Chaliye, let us start with the beginning. First of all, we will talk about what is heat transfer. Whenever there is a temperature difference, due to temperature difference, the heat will flow from high temperature to low temperature. Whenever there is a temperature difference, the heat will flow from high temperature to low temperature. Hi Shiva, welcome. Welcome to the session. What are the various modes of heat transfer? What are the various modes of heat transfer? Conduction, convection, and radiation. These are the modes of heat transfer. Conduction mode of heat transfer exists when the medium is stationary. Convection mode of heat transfer exists when the medium is dynamic, and radiation does not require a material medium. Radiation does not require a medium. So first of all, let us talk about the conduction. Which is the governing law for conduction? Conduction is governed by Fourier law. Conduction is governed by Fourier law. According to Fourier law, heat transfer rate due to conduction is given by minus Ka into dt by dx. dt by dx is the temperature gradient. That is the Fourier law. dt by dx is the temperature gradient in x direction. Okay, Shivam, welcome. How are you? Temperature gradient in x direction. Why there is a negative sign? In Fourier law, why there is a negative sign? Because dt by dx is negative. dt by dx is negative. And to make q as positive, minus is inserted. What is A? A is the area normal to the direction of conduction. Area normal to the direction of conduction. A is the area. I am all good. Shivam, I am also fine. So here we define the thermal conductivity. So K is the thermal conductivity of the material, which is the property. What is the unit of thermal conductivity? What is the unit of thermal conductivity? Either watt per meter Kelvin or watt per meter degree Celsius. thermal conductivity, which is the property of the material. This is how the conduction is defined. So the thermal conductivity varies with temperature. How the thermal conductivity varies with temperature? If we talk about the variation of thermal conductivity with temperature, temperature on x-axis, thermal conductivity on y-axis. For liquid and conductor, by increasing the temperature, thermal conductivity decreases, and for gas and insulator, by increasing the temperature, thermal conductivity also increases. This is how the variation of thermal conductivity takes place with temperature. Why it is so? Because in liquid, molecular diffusion is the governing factor, and in conductor it is free electron flow which governs the conduction. In case of a gas, molecular collision governs the conduction. Molecular collision. And in case of insulator, it is lattice vibration. And because of these factors, the variation of thermal conductivity is like this. The thermal conductivity of a gas is directly proportional to root T. The thermal conductivity where T is the absolute temperature. According to the kinetic theory of gas, we can find out the variation of thermal conductivity with temperature for a gas from the kinetic theory of gas. T is the absolute temperature. What is the meaning of absolute temperature? It must be in Kelvin. So this is how the thermal conductivity varies with temperature. Then the next mode of heat transfer is convection. Then the convection. What is the governing law for convection? Convection is governed by Newton's law. Convection is governed by Newton's law of cooling. Right? So according to Newton's law of cooling, Q convection is given by H into AS into delta T. Convection heat transfer rate, the unit is watt or joule per second, where AS is the surface area available for convection. Convection is a bulk phenomena. It is a surface phenomena. It occurs when the medium is dynamic. HAS delta T. Yes, Shivam. Very nice. Surface area available for convection. Surface area available for convection. What is delta T? Delta T is called bulk temperature difference. Bulk temperature difference. Delta T is equal to Ts minus T infinity if Ts is greater than T infinity, or it is T infinity minus Ts if T infinity is greater than Ts. Ts is the surface temperature, T infinity is the fluid free stream temperature, and H is called as convective heat transfer coefficient. H is known as, what is the unit of H? This gives the defining equation for H. Convective heat transfer coefficient. The unit is watt per meter square Kelvin or watt per meter square degree Celsius. Right? And one more important thing, convection is also defined as conduction plus bulk motion. There is conduction in no slip region. Convection is also called as conduction plus bulk motion of the fluid. And due to this, we can develop an expression for determining H. H is equal to minus thermal conductivity of the fluid into dt by dy in the fluid at the interface, that is y is equal to 0 upon delta t. Do you guys remember this expression or not? How many of you remember this expression? In the no slip region, the mode of heat transfer is conduction. कितने लोगों को ये expression पता है? It is very, very important to find out H. H is not a property. H is not a property of the fluid. It is experimentally determined complex parameter. H is experimentally determined complicated parameter. Right? And how to find out this dt by dy? To calculate dt by dy, we need temperature as a function of y in the fluid temperature profile. And how to get temperature profile from the velocity profile? So the analysis of convection is related with the fluid mechanics. Velocity profile is developed through fluid mechanics. Then we develop the temperature profile. And from the temperature profile, we can find out dt by dy in the fluid at y is equal to 0 to get the value of H, convective heat transfer coefficient. Clear? Then the third mode of heat transfer is, the next mode of heat transfer is radiation. Radiation is governed by Stefan-Boltzmann law. Radiation is governed by Stefan-Boltzmann law. According to the Stefan-Boltzmann law, heat transfer rate from an ideal black body is given by sigma into surface area into T to the power 4. AS is the surface area. Radiation is also a surface phenomenon. AS is the surface area. And T is the absolute temperature. That must be in Kelvin only. T is the absolute temperature. And sigma is known as, sigma is equal to 5.67 into 10 to the power minus 8. What is the unit of sigma? Watt per meter square Kelvin to the power 4. That is known as Stefan-Boltzmann constant. Boltzmann constant. ये तीन मोड ऑफ हीट ट्रांसफर है. These are the various modes of heat transfer. Clear? Then after that we talk about the energy conservation equation for the system. According to energy equation or energy conservation, according to energy conservation for the system, the heat transfer rate entering plus Q generated is equal to heat transfer rate leaving from the system plus Q stored. There are 4 terms involved in the energy conservation equation. If there is a system, there must be some heat entering into the system, there must be some heat leaving from the system, and there must be some heat generated in the system, and there will be some heat stored in the system. So Q in plus Q generated. What is the meaning of heat generation? Some other form of energy getting converted into heat energy, that is called as heat generation. Like chemical reaction. In case of chemical reaction, chemical energy converts into heat energy. Or in case of nuclear reaction, nuclear energy converts into heat energy. If some nuclear reaction is taking place inside the system, there is a heat generation. Or electrical energy can also be converted into heat energy. So these are some of the situations where the system is having a heat generation. How to write Q generation for the system? Q generation per unit time is equal to Q dot into volume of the system, where Q dot is rate of uniform heat generation per unit volume. Per unit volume. The unit is watt per meter cube. Q dot. Rate of uniform heat generation per unit volume. Heat entering into the system can be by conduction, convection, or radiation. Heat leaving from the system can be by conduction, convection, and radiation. And Q stored means rate of change of internal energy of the system. Rate of internal energy change, that is M into C into dt by d tau. Each and every term is having the same unit, that is joule per second or watt. MC dt by dt. So dt by dt, when temperature is a function of time, it means unsteady state system. When the system is in unsteady state, then there is a heat storage in the system. M into C into dt by dt. T for temperature and tau for time. So this is how energy balance can be done for a system. That is the energy conservation equation for the system. Clear? Anybody is having any doubt so far? So many questions are framed from this energy conservation equation. Sometimes Q generation is 0. When there is no mention about the generation of the heat, we will assume it as 0. Sometimes the system is said to be in steady state. It means Q storage will be 0. Temperature is independent of time. Sometimes heat entering into the system is 0, or sometimes heat leaving from the system is 0. So any 1, 2 or 3 terms can be 0, or we can use this expression to find the unknown term. उसके बाद detail. Hi Rishikesh, good evening, welcome. Now conduction in detail. Conduction in plane wall. Now let us discuss some formula for conduction in plane wall. What is the nature of temperature profile for conduction in plane wall? Plane wall means area is constant. If we develop the formula for conduction in plane wall, the first one is temperature profile. What is the nature of temperature profile? The nature of temperature profile is linear. T1 minus T upon T1 minus T2 is equal to X by L. The variation of temperature is linear. Next is heat transfer rate, K into A into delta T by L. That can be equated with delta T upon thermal resistance, where thermal resistance is given by L by Ka. What is the unit of thermal resistance? Kelvin per unit watt or degree Celsius per unit watt. RTH. And delta T is thermal potential, that is T1 minus T2. Yoga. These are the formula. K is the thermal conductivity. K is the thermal conductivity. A is the area normal to the direction of heat flow. L is the thickness of the system. These formula are valid, or we can also write one more formula. Q dash, that is Q by A, is equal to K into delta T by L, delta T upon A into RTH. This A into RTH is called as unit thermal potential. Sorry, unit thermal resistance. It is called as unit thermal resistance. Unit is meter square Kelvin per unit into RTH. Unit thermal resistance. Right? But these formula are valid only when if one-dimensional steady state conduction with no heat generation and the thermal conductivity is constant. If these assumptions are valid, then only this formula will be true. Conduction in plane wall. There is no heat generation, the thermal conductivity is constant, the conduction is one dimensional, and it is steady state conduction. Q dash is heat flux. Clear? But if K is variable If the thermal conductivity is variable, for K as a function of temperature, I have already talked about the variation of thermal conductivity as a function of temperature. If this is variable, then the temperature profile will not be linear. If K is variable, then temperature profile will not be linear. We can say dt by dx is inversely proportional to K. Will the heat transfer be constant or variable? Q will be constant. Q will remain constant because Q generation is equal to Q stored is equal to 0. As long as generation of heat is 0, storage of heat is 0, so we can say Q in is equal to Q out. That will be constant. That remains constant. So Q will be constant. Even if K is a variable, Q will be constant. So dt by dx, the slope of temperature profile will be inversely proportional to x. So the temperature profile will be something like this. This is the plane wall, let us say. This is x is equal to 0. This is the direction x. X is equal to L thickness. This is how the plane wall is. This is the plane wall. The heat is flowing from left to right. Here the temperature is T1. Here the temperature is T2. T1 is greater than T2. So the temperature profile will be like this. The temperature profile will be like this when K is given by K naught 1 plus beta T. The temperature profile will be like this when K is given by K naught 1 minus beta T. And the temperature profile will be straight line. The temperature profile will be the straight line only when K is constant. Only when K is constant, and the value of constant is, let us say, K naught. So this is how the temperature profile will be shown for variable thermal conductivity. For variable thermal conductivity, this is how the temperature profile looks like. Now for heat generation in plane wall, for uniform heat generation in plane wall, what is the nature of temperature profile? What is the meaning of uniform heat generation? Q dot is constant. The rate of heat generation per unit volume is constant. What is the nature of temperature profile? If there is a uniform heat generation, Q will not be constant. Here Q will not be constant. Temperature profile will be linear. For TS1 is equal to TS2. That is equal to TS. The temperature profile will be parabola. This is the plane wall. The temperature profile will be something like this, parabola. This is TS1, this is TS2. The temperature profile will be parabola, and at x is equal to L by 2, the temperature will be maximum. Here the temperature will be maximum and Q will be equal to 0. Q will be 0. The heat will flow in the first part towards left hand side, in the second part towards right hand side. For TS1 is equal to TS2, T is equal to Ts plus Q dot x by 2K into L minus x. This is how the temperature profile will look like. Temperature is a function of x square, that is parabola. Temperature profile will be parabola. And at x is equal to L by 2, dt by dx is equal to 0. Temperature is maximum. So how to write T maximum? T maximum is equal to Ts plus Q dot L square by 8K. That is the maximum temperature. And Q is directly proportional to X. That is linear. The variation of heat transfer rate will be linear. Q is a linear function of X. for uniform heat generation. If TS1 is not equal to TS2, for TS1 not equal to TS2, then we can write T maximum as if we use TS1 plus Q dot by 8K into 2L1 square, or we can write TS2 plus Q dot by 8K into 2L2 square. This is how we can write T maximum if TS1 is not equal to TS2. If TS1 is greater than TS2, then the temperature profile will be like this. This is T maximum. This is TS1. This is TS2. This distance is L1. This is L2. And for TS1 less than TS2, the temperature profile will be TS1 less than TS2. This is TS1. This is TS2. The temperature profile will be parabola like this. This is T maximum. This is L1. This is L2. Clear? Is this clear? कोई डाउट किसी को? That is for uniform heat generation in plane wall. For a hollow cylinder, conduction in hollow cylinder, what is the nature of temperature profile in case of hollow cylinder? Area is given by 2 pi RL, which is not constant. Area is not constant. So T1 minus T, first formula is T1 minus T upon T1 minus T2 is equal to, what is the nature of temperature profile? Fluid mechanics के भी formula आएंगे. On Saturday, I think. The nature of temperature profile will be parabola, logarithmic, ln of R by R1 upon ln of R2 by R1. That is the temperature profile. Temperature as a function of R is logarithmic. Q is given by 2 pi KL. It is given by 2 pi KL delta T upon ln of R2 by R1. That can be equated with delta T upon thermal resistance. I will try to cover everything, Vijay. We'll try to cover everything. So where the thermal resistance for conduction in hollow cylinder is equal to ln of R2 by R1 upon 2 pi KL. L is the length of the cylinder. The third formula is mean area. Next is mean area. Logarithmic mean area, that is A2 minus A1 upon natural log of A2 by A1. These formula are valid if conduction is one-dimensional steady state, no heat generation, and constant thermal conductivity. All the above formula are valid when that is called as logarithmic mean area. All the formula are valid when the conduction is one-dimensional steady state, constant thermal conductivity, and no heat generation. And for hollow sphere, for a hollow sphere, Again, area is given by 4 pi r square, which is not constant, which is variable. So for a hollow sphere, what is the temperature profile? What is the nature of temperature profile? The nature of temperature profile, temperature as a function of R is hyperbolic. What is the nature of temperature profile? Hyperbolic. The formula is given by this expression. And the rate of heat transfer Q is given by 4 pi K R1 R2 delta T upon R2 minus R1. That will be equated with delta T upon thermal resistance. So where thermal resistance in case of hollow sphere is given by R2 minus R1 upon 4 pi K R1 R2 watt per Kelvin. Kelvin per watt, sorry. The unit of thermal resistance is Kelvin per unit watt, not watt per Kelvin. And the third formula is geometric mean area of the hollow sphere, that is under root of A1 A2, where A1 is equal to 4 pi R1 square and A2 is equal to 4 pi R2 square. In the previous slide, A1 and A2, A1 is 2 pi R1L and A2 is 2 pi R2L. These are valid in case of all these formula are valid when conduction is one-dimensional steady state, valid for one-dimensional steady state heat conduction. Conduction with no heat generation and constant thermal conductivity. All these formulas are valid in this situation. Now, uniform heat generation in case of a cylinder and sphere. Now, if there is a heat generation, uniform heat generation, what is the nature of temperature profile? Whenever there is a heat generation, Q dot is constant. That is why Q will not be constant. Q will become variable. For uniform heat generation, the temperature profile will parabola. One is for solid cylinder. For a solid cylinder, T is given by Ts plus Q dot by 4K into R square minus small r square. And at R is equal to 0, dt by dr is equal to 0. So T is maximum. And we can say T maximum is given by Ts plus Q dot into R square by 4K. For solid sphere, the rate of heat transfer is directly proportional to R square. Q is directly proportional to R square. Because dt by dr is, as dt by dr is directly proportional to R. For a hollow sphere, solid sphere having uniform heat generation, this is parabola. For solid sphere, T is given by Ts plus Q dot by 6K into R square minus small r square. It is also parabola. Whenever there is a heat generation, the temperature profile will be parabola. And at R is equal to 0, T is maximum. And T maximum is calculated as Ts plus Q dot R square by 6K. and Q is directly proportional to RQ. The rate of heat transfer is proportional to RQ because Q is given by minus K into area 4 pi R square into dt by dr. So dt by dr is directly proportional to R. Here Q is given by minus K into 2 pi RL into dt by dr. And dt by dr is directly proportional to R. 1 R is already there. Here R square is there. So Q is proportional to R cube in case of sphere. बताइए, is this clear up to this point? Are these formula clear? Then combined modes of heat transfer. What is the meaning of combined modes of heat transfer? Conduction, convection, and radiation. The combined modes of heat transfer is analyzed by circuit diagram, electrical analogy. So for conduction, R conduction is given by L by Ka. For plane wall, or ln of R2 by R1 upon 2 pi KL. For hollow cylinder, and R2 minus R1 upon 4 pi K R1 R2 for sphere. This is conductive resistance, and R convection is given by 1 upon H into AS, because Q is equal to HAS into delta T. If we equate with delta T upon thermal resistance, then we will get 1 upon HA. That is the convective thermal resistance. Similarly, radiative thermal resistance. One upon HR into AS, where HR is the radiative heat transfer coefficient. Watt per meter square Kelvin. Now, based on these modes of heat transfer, we can draw the circuit diagram, and the circuit diagram can have series combination or can have parallel combination. The circuit diagram can be arranged, can have series combination or parallel combination. For series combination of resistances, हम बोल सकते हैं Q will be equal to Q1 is equal to Q2 is equal to constant. Q will remain same. Delta T overall is equal to delta T1 plus delta T2 plus so on. So R equivalent thermal resistance is R1 plus R2 plus R3 and so on. And delta T1 by delta T2 is equal to R1 by R2. This is for series resistance. And for parallel combination of resistance, Q is equal to Q1 plus Q2 plus Q3 and so on. And delta T overall is same as delta T1 is equal to delta T2 is equal to constant. So 1 upon R equivalent will be equal to 1 by R1 plus 1 by R2 plus so on. And Q1 upon Q2 is equal to R2 by R1. This is for parallel combination of resistance. For composite plane wall, with convective environment, composite means made up of more materials. For composite plane wall with convective environment, R equivalent is equal to 1 upon A into 1 upon Hi plus summation of J is equal to 1 to N Lj by Kj plus 1 upon H naught. That is R equivalent, and Q is given by delta T overall upon R equivalent, that can be equated with U into A into delta T overall. Q remains constant. So from here we can write delta T overall thermal potential is Ti minus T naught. That is called as overall thermal potential. Overall thermal potential. यहाँ से U into A into R equivalent will be equal to 1, or we can say U is equal to 1 upon A into R equivalent. That is called as overall heat transfer coefficient. For composite plane wall involving combined modes of heat transfer, we define the overall heat transfer coefficient. The unit is watt per meter square Kelvin. That is called as overall heat transfer coefficient. Similarly, composite cylinder with convective environment, we can say Q is equal to delta T overall upon R equivalent is equal to Ui into Ai into delta T overall. Inner overall heat transfer coefficient is equal to U naught into A naught into delta T overall, where Ai is equal to 2 pi R1L and A naught is equal to 2 pi Rn plus 1 into L. So from here we can say Ui into Ai into R equivalent will be equal to U naught into A naught into R equivalent is equal to 1. And R equivalent will be and how to write R equivalent? R equivalent will be 1 upon 2 pi L 1 upon Hi into R1 plus summation of J is equal to 1 to N ln of Rj plus 1 upon Rj upon Kj plus 1 upon H naught into Rn plus 1. This is how we can find out Ui and U naught. That is for composite cylinder with convective environment. Clear? Again, composite sphere. Similar to that, we can write composite sphere with convective environment. For a sphere, Q is equal to Ui into Ai into delta T overall is equal to U naught into A naught into delta T overall is equal to delta T overall upon R equivalent. That remains constant. And Ai is equal to 4 pi R1 square and A naught is equal to 4 pi R n plus 1 square. Total layers is n. So from here Ui into Ai into R equivalent is equal to U naught into A naught into R equivalent will be equal to 1. We can find out Ui and U naught if we know R equivalent, where R equivalent is given by 1 upon 4 pi then 1 upon Hi into R1 square plus summation of J is equal to 1 to N Rj plus 1 minus Rj upon Kj Rj Rj plus 1 upon H naught into Rn plus 1 square. This will be equivalent resistance. Then critical insulation. Critical insulation to increase the rate of heat transfer. What is the critical radius of insulation? Critical radius of insulation for a cylindrical system is given by, what is the formula for critical insulation? Critical radius of insulation for a cylinder. What is the critical radius of insulation? बताइए. बताइए बताइए जल्दी. I am waiting. Simple है. The topic critical thickness of insulation is very simple, but highly important from your examination point of view. K by H, K insulation by H outside. K by H. Critical radius of insulation is given by K by H. K is the thermal conductivity of the insulating material. The unit is watt per meter Kelvin. The unit of H is watt per meter square Kelvin. So RCR will give you what is critical radius of insulation, where Q becomes maximum. The rate of heat transfer becomes maximum. For a sphere, critical radius of insulation for a sphere will be 2K by H. 2K by H for a sphere. Critical radius, and critical thickness of insulation is given by RCR minus R naught. Sometimes the question can be asked about the critical thickness of insulation. Thickness of insulation. Critical thickness of insulation. We can say if R naught less than RCR, as insulation increases, the heat transfer rate increases first and then Q decreases. For R naught greater than equal to RCR, as insulation increases, the rate of heat transfer decreases continuously, isn't it? If the outer radius is less than critical radius of insulation, if the outer radius is less than critical radius of insulation, so by increasing the insulation, Q will increase first, become maximum, and then decrease. Q will become maximum corresponding to RCR, and then Q will decrease. But if R naught is already equal or greater than RCR, then by increasing the insulation, the rate of heat transfer decreases continuously, isn't it? That is one method for increasing the rate of heat transfer. There is one more method for increasing the rate of heat transfer, that is the fin theory. By using the fins, there are three types of fins. Very long fin, then short fin with insulated tip, and the third one is short fin with free tip or convecting tip. So for long fin, when L is very large, L is infinite, the heat transfer rate is given by, or the temperature profile. What is the nature of temperature profile for very long fin? theta upon theta s, that is T minus T infinity upon Ts minus T infinity, is given by e to the power minus mx. So temperature as a function of x is exponential. What is the nature of temperature profile? Temperature profile is exponential, where m is, it is exponential. Yes, Shivam. What about others? Do you guys know what is the m? What is the unit of m? M is under root of hp by k into AC. What is the unit of m? M is called a spin constant. What is the unit of spin constant? T infinity is the free stream temperature of the fluid. Ts is the surface temperature. T is the temperature at any x. What is the unit of m? No, it is not unitless. No, it is not unitless. Unit is m meter to the power minus 1, 1 by meter. M0, L minus 1, T0. That is the unit of m. H is the convective heat transfer coefficient, P is the perimeter, K is the thermal conductivity, AC is the cross-sectional area of the fin. Q fin is given by K A M theta S, or we can write it as under root of HP Ka into theta S. So here we can say Q fin is directly proportional to root K. That is heat loss from the fin. For very long fin, these are the formula for very long fin. And then we talk about the fin efficiency. Fin efficiency. That is Q fin upon Q maximum. The heat loss is maximum when the entire fin is maintained at the base temperature. That is H into PL into theta S. That is Q maximum. So we can say efficiency of the fin is given by KAM theta S upon H into PL into theta S. If you solve this, then efficiency of the fin is given by 1 upon ml. 1 upon ml, which is always less than 1. Fin efficiency. Then fin effectiveness. That is Q fin divided by Q without fin. It can be less than, it can be greater than 1. Where Q without fin is H into AC into theta S. So we can say effectiveness for the fin, for very long fin, effectiveness is given by Km by H, which is less than equal to greater than 1. This is fin effectiveness. Which is the economic performance. And this is called as efficiency of the fin efficiency. Which gives the thermal performance of the fin. Thermal performance. For short fin with insulated tip, with insulated tip. For the short fin with insulated tip, what is the nature of temperature profile? Theta upon theta S, that is T minus T infinity upon Ts minus T infinity, is given by cos hyperbolic M L minus X upon cos hyperbolic ML. That is temperature as a function of X is hyperbolic. The variation of temperature is hyperbolic. At X is equal to L, theta is minimum or T is minimum or maximum. So theta minimum upon theta s is equal to, if you put x is equal to L, then cos hyperbolic 0 is 1 upon cos hyperbolic ML. That is first formula. The second is Q fin is equal to KAM theta s into 10 hyperbolic ML, or we can write it as under root of HP KA into theta s 10 hyperbolic ML. Fin efficiency, that is 1 upon ML into 10 hyperbolic ML, and fin effectiveness is given by Km by H into 10 hyperbolic ML. These are the formula for short fin with insulated tip. Short fin with insulated tip. And for the last case, short fin with free tip, for short fin with free tip, L is replaced by LC, that is called as corrected length. L will be replaced by LC in previous formula. Previous formula. What is LC? How to calculate LC? LC is equal to L plus AC by P. That is the corrected length. So theta upon theta s can be written as cos hyperbolic M LC minus X upon cos hyperbolic M LC. That is how we can find out the temperature profile. Hyperbolic. Q fin is equal to KAM theta s 10 hyperbolic MLC. Efficiency of the fin 1 upon ML LC into 10 hyperbolic MLC. Effectiveness of the fin is equal to Km by H into 10 hyperbolic MLC. This is how we can find out the various parameters using the corrected length. These are the formula for fin theory. One more important concept regarding the fin theory. When a bar is connected to two heat sources like this, when a bar is connected to two heat sources at the same temperature, Ts and Ts, then the temperature profile will be like this. Using the fin theory, the temperature profile will be something like this. This is T infinity. This is Ts, this is Ts. Temperature is minimum at X is equal to L by 2. The temperature will be minimum at X is equal to L by 2. For Ts1 greater than Ts2, if Ts1 is greater than Ts2, the curve will be like this. The temperature profile will be something like this. The temperature profile will be something like this. Here the temperature is minimum. X is greater than L by 2. And the last part in the unsteady state conduction is unsteady state conduction. What is unsteady state conduction? When the temperature is a function of time, then the system is in unsteady state. The conduction is unsteady state when the temperature is a function of time. For the conductive thermal resistance is very, very less compared to convective thermal resistance. Or Biot number is very, very less than 1. Or K is very large and H is finite. If the Biot number is less than 0.1. 0.1. Or we can say for R conduction to be less than equal to 1/10 of R convection. Or Biot number. What is Biot number? That is the ratio of conductive thermal resistance to the convective thermal resistance. That is Biot number. So Biot number is less than 0.1. So the analysis is called as lumped system analysis. It is called as lumped system analysis. Why do we call it as lumped system analysis? Because in this case, temperature is a function of time only. In this case, temperature will be a function of time only. Lump analysis. Temperature will not be a function of space. Temperature will not be a function of x. It is a function of time only. So then some formula regarding the lump system analysis. First formula is the temperature profile theta upon theta I, that is T minus T infinity upon Ti minus T infinity, is equal to e to the power minus HA by rho CV into tau. Or we can write it as e to the power minus B into tau. Or we can write it as e to the power minus tau upon tau star. Or we can write e to the power minus Biot number into Fourier number. Theta is the initial temperature difference. And HA by rho CV into tau is equal to B into tau. Is equal to B into tau. Is equal to tau upon tau star. Is equal to Biot number into Fourier number. Is equal to minus ln of theta by theta I. These are the formula. What is Biot number? I have already told you about the Biot number. Here Biot number is given by R conduction upon R convection. That is H into LC by K, where LC is equal to volume upon surface area. And the Fourier number is given by Q conduction upon Q stored. That is alpha tau by LC square. That is the Fourier number. These are Biot number and Fourier number. These are dimensionless numbers. Dimensionless. Biot number and Fourier number. And B is HA by rho CV. That is called as thermal. That is called as thermal response of the system. The unit is second inverse. M0 L0 T minus 1. HA by rho CV. B is thermal response of the system. From the energy conservation equation, we can say Q tau is equal to HA into T minus T infinity is equal to minus rho CV into dt by d tau. That is the rate of heat transfer. Heat lost is equal to energy storage. Energy balance equation at any instant. At any instant tau. And initial condition Q0 is equal to H into AS into Ts minus T infinity or Ti minus T infinity. Initial temperature Ti is equal to minus rho Cv into dt by d tau at tau is equal to 0. That is the initial condition. Q maximum is equal to M into C into Ti minus T infinity, and Q 0 to tau is equal to yes. Q0 to 2 is M into C into T minus T infinity. That is equal to that is Q maximum into 1 minus e to the power minus HA by rho CV into tau. क्या लैग हो रहा है क्या? लैग नहीं है. So these are some of the formula for unsteady conduction, unsteady state conduction or lump analysis. Next, we will discuss some formula for convection. Then we will talk about some formula for convection mode of heat transfer. Convection. Convection is either forced or artificial, or another is free or natural convection. Forced or artificial, free or natural convection. First of all, let us talk about the forced convection. Forced convection. In case of forced convection, pressure gradient and buoyant force, pressure gradient and inertia force develop the fluid motion. So in case of forced convection, Nusselt number is directly proportional to, is given by a function of Nusselt number is given by a function of Reynolds number into a function of Prandtl number. What is Nusselt number? Nusselt number is given by R conduction upon R convection, like Biot number. The only thing is conduction is for the fluid and the convection is for the fluid. Conductive resistance and convective resistance both are for the fluid. So Nusselt number is H into L by Kf, thermal conductivity of the fluid. That is the Nusselt number. And Prandtl number is kinematic viscosity upon alpha. That is mu Cp by Kf. That is the Prandtl number. And Reynolds number is the ratio of inertia force upon viscous force. The ratio, yes, Biot number is for solid and Nusselt number is for the fluid. Conductive resistance, or we can call it as Q convection in the fluid divided by Q conduction. The ratio of convective heat transfer rate to the conductive heat transfer rate. Reynolds number is the ratio of inertia force to viscous force. These are the three dimensionless numbers which define force convection. So in case of force convection, first of all, we will talk about external force convection. When the flow is external flow, that is development of boundary layer theory. The boundary layer theory will be developed over the flat surface. It will be like this. A and B. One is laminar boundary layer, another is turbulent. This is turbulent. This is laminar. So in external force convection, if Prandtl number is less than equal to greater than 1, or in case of external force convection, Prandtl number will decide. If Prandtl number is less than 1, then delta V will be less than delta T. Velocity boundary layer thickness, delta V is the velocity boundary layer thickness, will be less than thermal boundary layer thickness. Let me first write. And delta T is the thermal boundary layer thickness. So for laminar flow, when the flow is laminar, when the Reynolds number is less than 5 into 10 to the power 5. When the Reynolds number is less than 5 into 10 to the power 5, then if Prandtl number is less than 1, then delta V will be less than delta T. If Prandtl number is equal to 1, then delta V is equal to delta T. If Prandtl number is greater than 1, then velocity boundary layer thickness is greater than thermal boundary layer thickness. Then thermal boundary layer thickness. For laminar force convection. For laminar flow. And delta V is given by 5x upon under root of Rex. Implies delta V is directly proportional to root x. Another formula for laminar boundary layer. Delta V by delta T is equal to Prandtl number to the power 1 by 3. Delta V by delta T is Prandtl number to the power 1 by 3. Local drag coefficient tau naught upon rho u infinity square by 2 is equal to 0.664 upon under root of Reynolds number. Nusselt number is directly proportional to Reynolds number to the power 1 by 2 into Prandtl number to the power 1 by 3. These are some of the formula. And average Nusselt number is given by twice of Nusselt number at x is equal to L. Average convective heat transfer coefficient twice of convective heat transfer coefficient at x is equal to L. Average drag coefficient is twice of CF at x is equal to L. From here we can say H is proportional to x to the power minus 1 by 2. For turbulent boundary layer, For turbulent boundary layer, when the Reynolds number is greater than 5 into 10 to the power 5, when the Reynolds number is greater than 5 into 10 to the power 5, in that case, delta V is equal to delta T is 0.376 upon REX to the power 1 by 5. It is independent of Reynolds number, Prandtl number. They are not related with Prandtl number. Delta V is equal to delta T if the boundary layer is turbulent. For turbulent boundary layer, local drag coefficient 0.059 upon REX to the power 1 by 5 and CD is equal to 5 by 4 CF at X is equal to L. Nusselt number is proportional to Reynolds number to the power 4 by 5 into Prandtl number to the power 1 by 3. So average Nusselt number is equal to 5 by 4 into Nusselt number at X is equal to L. Average convective heat transfer coefficient is equal to 5 by 4 into H at X is equal to L. From here we can say H is proportional to X to the power minus 1 by 5. It will be X also na here. It will be 0.376 X. Then internal force convection. Then internal force convection. Flow in a pipe. Flow in pipe or duct. In that case, Reynolds number is defined as rho into average velocity into hydraulic diameter upon by mu, where dH is the hydraulic diameter 4A by P. That is called as hydraulic diameter. That is the hydraulic diameter. And average velocity is given by 2 upon R square integration 0 to R U into R into dr. And mean temperature, average temperature of the fluid is given by 2 upon V average into R square integration 0 to R U into T into R dr. And for laminar flow, this average temperature, or we can call it as bulk mean temperature, TB. Bulk mean temperature at any section. For laminar flow, Nusselt number is given by H into dH by Kf is constant. The value of constant is 4.36 for Q dash as constant, for constant heat flux, and it will be 3.66 for Ts to be constant. So H is independent of, H is directly proportional to D to the power minus 1. H is inversely proportional to D. That is for laminar boundary layer. For turbulent flow, the flow is laminar when the Reynolds number is less than 2000. The flow will be turbulent when the Reynolds number is greater than 4000. So here Nusselt number is given by 0.023 into Reynolds number to the power 4 by 5 into Prandtl number to the power 1 by 3. So implies H is proportional to D to the power minus 1 by 5. That is for turbulent boundary layer. Turbulent flow in a pipe. ठीक है, समझ में आ रहे हैं ये सब फॉर्मूले हैं. You need to memorize this formula. For natural or free convection, for natural convection, Nusselt number is given by a function of Grashof number into a function of Prandtl number. Here there is a Grashof number. In natural convection, due to density gradient, there is a bind force develops. Density gradient develops the bind force, which makes the fluid to move. Bind force. These parameters make the fluid to move. So Grashof number is given by, here the Grashof number is given by the ratio of bind force to viscous force. In place of Reynolds number, it will be Grashof number in case of natural convection. That is given by rho square G beta delta T x cube by mu square. That is the formula for Grashof number. Or we can write G beta delta T x cube, that is called as local Grashof number, upon kinematic viscosity square. That is called as local Grashof number. That is the local Grashof number. Where rho is the density, G is the acceleration due to gravity, X is the distance from the leading edge, beta is coefficient of thermal expansion. It is called as coefficient of thermal expansion. The unit is Kelvin inverse. So for ideal gas, beta is given by 1 by absolute temperature. That is the film temperature, where T film is equal to Ts plus T infinity by 2. That is beta. Beta is the coefficient of thermal expansion and X is the distance from the leading edge. And average Grashof number is given by rho square G beta delta T LC cube by mu square, or we can write it as G beta delta T LC cube by kinematic viscosity square. That is the average Grashof number. That is called as average Grashof number. Delta T is the bulk temperature difference. Delta T is bulk temperature difference, and LC is called as characteristic length. Characteristic length. What is the characteristic length? The distance over which boundary layer is allowed to grow. Allowed to grow. And that is, LC is the vertical dimension. In case of vertical surface, it is the vertical dimension. The boundary layer is growing on the vertical surface. Vertical dimension or vertical projected dimension or vertical projection. In case of horizontal surface, for horizontal surface, if there is no vertical dimension, then LC will be equal to area by perimeter. Area by perimeter. That is about the Grashof number. And for laminar motion, for laminar boundary layer, when the Grasov number is less than 10 to the power 9, for laminar boundary layer, when the Grasov number is less than 10 to the power 9, Nusselt number is proportional to Grasov number into Prandtl number to the power 1 by 4. And for turbulent boundary layer, in case of natural convection, for turbulent boundary layer, when the Grasov number is greater than 10 to the power 9, then Nusselt number is proportional to Grasov number into Prandtl number to the power 1 by 3. These formula you need to remember. That is all about the convection, formula for convection. Important formula for convection. And Grasov number multiplied by Prandtl number is called as Rayleigh number. We can also use the Rayleigh number. Clear? Now, some formula for the heat exchanger. Heat exchanger. From the energy conservation equation, Q is equal to CH into delta TH is equal to CC into delta TC is equal to U into A into LMTD is equal to effectiveness into Q maximum. That is the thermal capacity of the heat exchanger or heat load or thermal capacity of the heat exchanger. What is CH? Where capital C is equal to mass flow rate into specific heat. That is called as heat capacity rate. Heat capacity rate. The unit is watt per Kelvin. And delta TH, C is the specific heat at constant pressure, that is joule per kg Kelvin. And delta TH is equal to TH1 minus TH2. Delta TC is equal to TC2 minus TC1. U is the overall heat transfer coefficient. A is the area of the heat exchanger. Epsilon is the effectiveness. Q maximum is given by C minimum into TH1 minus TC1. Where C minimum is equal to minimum among CH and CC. Heat capacity rates. That is one way. And what is LMTD? LMTD is given by delta T1 minus delta T2 upon natural log of delta T1 by delta T2. Delta T1 by delta T2. For parallel flow heat exchanger, temperature profile will be like this. Hot fluid, cold fluid, that is parallel flow. So this is delta T1, this is delta T2, TH1, TC1, TH2, TC2. So LMTD for parallel flow heat exchanger, mean temperature difference for parallel flow heat exchanger, TH1 minus TC1, that is delta T1, minus TH2 minus TC2 upon natural log of TH1 minus TC1 upon TH2 minus TC2. For counterflow heat exchanger, this is delta T1, this is delta T2, This is TH1, TH2, TC1, TC2. So for counterflow heat exchanger, LMTD will be is equal to TH1 minus TC2 minus TH2 minus TC1. That is for counterflow heat exchanger upon natural log of TH1 minus TC2 upon TH2 minus TC1. These are the formula. And if there is a special case for complex heat exchanger or a special case of counterflow, for counterflow heat exchanger, if CH is equal to CC or delta TH is equal to delta TC, in that case LMTD will be equal to TH1 minus TC2 or TH2 minus TC1. In that case, the temperature profile will be straight lines. The temperature profile will be straight line like this. So this is delta T1, this is delta T2. For counterflow, and for complex heat exchanger, LMTD will be given by the correction factor into LMTD for counterflow heat exchanger, where F is less than 1. What is complex heat exchanger? Cross flow or multi-pass. Multi-pass heat exchanger. So what we can say here is, for same terminal temperatures, same terminal temperatures, LMTD for counter is maximum, then LMTD for complex, and finally LMTD for parallel. This is the order of LMTD for the same terminal temperatures. Now, effectiveness in terms of NTU. So effectiveness for parallel flow heat exchanger 1 minus e to the power minus n 1 plus c upon 1 plus c. Effectiveness for counterflow 1 minus e to the power minus n 1 minus c upon 1 minus c e to the power minus n 1 minus c. These are the formula where NTU is given by U into A by C minimum, and C minimum is minimum among CH and CC, and C is equal to C minimum by C maximum. These are the formula. For C is equal to 0, so it is boiler or condenser, evaporator or condenser. When there is a phase change, C will be 0. If C is equal to 0, effectiveness for parallel is equal to effectiveness of counter is equal to effectiveness of complex. All will be same. That will be 1 minus e to the power minus n for C is equal to 0. If C is equal to 1, for C is equal to 1, implies C minimum is equal to C maximum, or CH is equal to CC, or delta TH is equal to delta TC. If this is the case, then for parallel flow heat exchanger, it will be 1 minus e to the power minus 2n by 2. For counter flow heat exchanger, we use L'Hospital rule. So effectiveness for counterflow, when C is equal to 1, then it will be NTU upon NTU plus 1. That is important. And for complex heat exchanger, here effectiveness for complex heat exchanger is correction factor multiplied by effectiveness per count. These are some more formula from the heat exchanger. And the last one is radiation mode of heat transfer. The next one is radiation. Next is radiation. The first formula is J is equal to epsilon EB plus G. This is the relation watt per meter square. Flux. Radiosity is equal to emissive power plus E plus rho G, sorry. E plus rho G. So here J can be less than equal to greater than G. J is the total radiation leaving from the surface and G is the insulation. If J is greater than G, then there will be net heat loss. That is Q by A is equal to J minus G. If J is less than G, then it will have net heat gain Q by A gain. Here it will be loss, here it will be gain. Net heat gain will be equal to G minus J. And if J is equal to G, there is no heat gain or loss. It means Q by A is equal to 0. And also alpha plus rho plus tau is equal to 1 for all the surface emitting any type of radiation. From the energy equation we can say sum of alpha plus rho plus tau is equal to 1 for any surface emitting any type of radiation. Then the shape factor. Shape factor F. F1 to 2 is given by Q1 to 2 upon Q1. Reciprocity theorem A1 F1 to 2 is equal to A2 F2 to 1. That is called as reciprocity theorem. Then enclosure theorem F11 plus F12 plus so on is equal to 1. That is called as enclosure theorem. For an enclosure, we can apply the enclosure theorem. We can apply symmetry principle. We can use, and for self shape factor. Self shape factor. F1 to 1. F1 to 1 is equal to 0 for convex surface. F1 to 1 is equal to 0 for flat surface. F1 to 1 is equal to non-zero for concave surface. Self shape factor for concave surface is non-zero. Now the radiation laws. The variation laws of radiation. One is called as Planck distribution law. That is for E lambda B. Monochromatic emissive power for the black body. It is defined for determining the monochromatic emissive power for the black body. Stephen Boltzmann law. That is for total emissive power for the black body, that is integration of E lambda B into D lambda, that is given by sigma into T to the power 4. That is Stephen Boltzmann law. Then wind displacement law. According to this, lambda maximum into absolute temperature is constant, or we can say lambda maximum is inversely proportional to temperature, absolute temperature. That is called as wind displacement law. Then Kirchhoff's law of radiation. Alpha is equal to epsilon for temperature to be constant. Alpha and epsilon are equal for thermal equilibrium. Yes, PDF will be provided, Alok. PDF will be provided to you. Lambert cosine law for intensity in a particular direction is directly proportional to cos theta. Theta is the angle with normal. Then the analysis of the radiation. Last one is radiation analysis. For black body, between black body radiation analysis or radiation heat exchange. Between black bodies, there is a space resistance defined R1 to 2, that is 1 upon A1 F1 to 2 is equal to 1 upon A2 F2 to 1. That is called as space resistance. Space resistance, meter to the power minus 2. Alok, solid angle is this angle. This is the, if it is a cone, then this cone angle is the solid angle, 3-dimensional angle. This is the solid angle. The angle subtended by the surface at the center of other surface, that is called as solid angle. Between black bodies, Q1 to 2 net is given by delta EB upon RS, or we can write it as sigma into T1 to the power 4 minus T2 to the power 4 upon 1 upon A1 F1 to 2. That is Q1 to 2 net. For non-black bodies, other than space resistance, there is a surface resistance defined. That is 1 minus epsilon upon epsilon A. That is called as surface resistance. Epsilon upon epsilon A. So for non-black bodies, Q1 to 2 net is equal to delta EB upon R1 plus R1 to 2 plus R2. So that will be equal to sigma into T1 to the power 4 minus T2 to the power 4 divided by 1 minus epsilon 1 upon epsilon 1 A1 plus 1 upon A1 F1 to 2 plus 1 minus epsilon 2 upon epsilon 2 A2. This is the formula for net heat loss between non-black bodies, net heat exchange between the non-black bodies. Or we can write it as Q1 to 2 net is equal to sigma into A1 into T1 to the power 4 minus T2 to the power 4 divided by 1 minus epsilon 1 upon epsilon 1 plus 1 upon F1 to 2 plus A1 by A2 into 1 minus epsilon 2 upon epsilon 2. This is the formula for non-black bodies. F12 is the shape factor. It is not the correction factor. It is called as radiation shape factor. F1 to 2 is the shape factor from 1 to 2. What is shape factor? The fraction of radiation leaving from surface 1 and reaching 2. That is called as shape factor from 1 to 2. And F2 to 1 implies that the fraction of radiation leaving from 2 and reaching 1. They are known as shape factor, orientation factor, view factor. Now for infinitely large parallel plates, A1 is equal to A2 is equal to A, and F1 to 2 is equal to F2 to 1 is equal to 1. So Q1 to 2 net will become sigma into A into T1 to the power 4 minus T2 to the power 4 upon 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. This will be the expression for infinitely large parallel plates. Correction factor is not in radiation heat transfer. Correction factor is in heat exchanger. LMTD correction factor, that is different thing. For concentric cylinders, A1 is equal to 2 pi R1L, A2 is equal to 2 pi R2L, and F1 to 1 is equal to 0, F1 to 2 is equal to 1. So Q1 to 2 net will become sigma into 2 pi R1L into T1 to the power 4 minus T2 to the power 4 upon, it will be 1 upon epsilon 1 plus R1 by R2 into 1 minus epsilon 2 by epsilon 2. This is the expression. For concentric space, configuration factor is same as shape factor. There is one more term, gray shape factor or interchange factor. For concentric sphere, A1 is equal to 4 pi R1 square and A2 is equal to 4 pi R2 square. So Q1 to 2 net, here F1 to 1 is equal to 0 and F1 to 2 is equal to 1. Q1 to 2 net will be equal to sigma into 4 pi R1 square into T1 to the power 4 minus T2 to the power 4 upon 1 by epsilon 1 plus R1 square by R2 square into 1 minus epsilon 2 upon epsilon 2. So there is a term called gray shape factor or interchange factor. How to find out the gray shape factor? We can write the general expression Q1 to 2 net as sigma into A1 into Fg into T1 to the power 4 minus T2 to the power 4. Here in this expression, Fg is called as gray shape factor or interchange factor. Gray shape factor, or we can call it as interchange factor. So if we compare these, then we will get the expression for gray shape factor, interchange factor. The PDF will be provided in the Telegram group. PDF will be provided to our Byjus Telegram group. And to join the Telegram group, you can have the link in the description box. Please go through the description box of this session. You will find all the important links. Everyone, Please go through the description link box. You will find the links for all the important links, like joining the Telegram group or free content. Now the radiation shield. If there are n number of radiation shield, for n number of radiation shield, so Q122 net is given by, for n radiation shields, it is given by sigma into A into T1 to the power 4 minus T2 to the power 4 divided by 1 upon epsilon 1 plus 2n by epsilon 3 plus 1 upon epsilon 2 minus n plus 1. For n radiation shield, A1 is equal to A2 is equal to A3 is equal to A. F1 to 2 is equal to F1 to 3 is equal to F2 to 3 is equal to 1. So this is the expression. For epsilon 1 is equal to epsilon 2 is equal to epsilon 3 is equal to epsilon. For all the emissivities are same, that is for n shield. If all the emissivities are same, then Q for n shield will be equal to 1 upon n plus 1 into Q without shield. N is the number of shields. N is the number of shields. So what we can say, the page is also complete. So what we can say, that Q n shield divided by Q without shield is equal to 1 upon n plus 1. That is all about, these are the important formula from the heat transfer subject. So I will bring such type of session for fluid mechanics also very soon, either on Saturday or in the next couple of days. So I hope you guys have enjoyed it and you guys have understood, or you guys have revised the formula. So try to go through this PDF to improve your understanding, to improve your formula. So with this note, let me take your leave. Enjoy, take care, have a good night, stay safe and stay motivated. Thank you guys. Thank you very much for being there throughout this session. Thanks a lot.